Alright, in this video we're going to be working some vector field problems. And this is when we first learned about vector fields in the plane. We're going to sketch them, we're going to determine if they're conservative, and then we're going to, if so, find a potential function for them. So I guess we're going to start with some sketching. Okay, so f of x and y is 1 and 1 at all x and y. So it's that any point I'm going over 1 up 1. So maybe here, going over 1 up 1. And so I just need to pretty much replicate that vector a few other places. Oh, maybe it was a little long, but that's the idea. Same length, same trajectory, just everywhere. Okay, number 2 is f of x and y is equal to x and y. That might be a little tough to draw. Okay, so let's start at the point where x is 1 and y is 0. Well, then I'll just go another 1 and nowhere in y. Okay, at, say, the point 3, 0, it's just going to get longer. And then over here where it's 1 and 1, well, I'll just have 1 and 1 again, so it'd be like that. 2 and 1 would go farther over, but the same amount up. 0 and 1 would go like that. Basically, it's just going to keep going along the trajectory of like on the line that starts at the origin and goes to that point, each time. So I'm just looking kind of like, okay, maybe I'll like that. Go down here. Whoops. I should have been in line with that. But that's the general idea. It's going to kind of like radially expand outwards. Something about like that. Okay, I think that's a good enough sketch. The third one is f of x and y is equal to x and 0. So, okay, when x is equal to 1, the vector is going to be 1 and 0, right? Because it doesn't depend on y. So, probably should have been copying this down each time. Okay, so when x is equal to 1, any point where x equals 1, the vector is going to be 1, 0. Then I might go over here and go to where x is a little bit bigger. And well, where x would be bigger, this coordinate would be a little bit bigger, and this would be a longer vector. So I don't know, maybe something like that. A few of these. And maybe over here where x is negative but small, I'd have a short vector. And over here where x was more negative, then it would be longer and also pointing in that direction. So maybe something like this. Alright, those weren't the best arrows. Alright, the next one is f is 0 and x. So pretty much whatever the x coordinate is, that's what the y component of the vector output's going to be. So over here where x is equal to 1, okay, I'm going to be going 1 unit in y. Okay, when x is 2, I'm going to go twice as far. That's about like that. Okay, and then over here I could, give another one. It's the same length. Then over here would be pretty much the same thing, but negative. Okay, so go down to -1. And then over here where x is a little more negative, the vector would be longer. About like that. That would be a good vector field there. got 0, 1. And so at a given y coordinate, we're just always going to have the same vector. So y equals 1, I'm going to have the vector 0, 1. So
do you like get some type of
yeah, and then down here where, you know, y is smaller, it's just going to be a shorter vector. Okay, and, well, that doesn't, no, that's not it. Let me get an eraser. Yeah, right. If I'm on the x-axis, that's where y is 0, and I'd have no vector at all. Let's try that again. I'm going to put a little separation between the axes, and then I'll draw some little short vectors. Okay, down here, this would also be really small. And then when I got more negative, the vectors would get longer. Something about like that. Okay. The last one of the sketch of vectors is y and 0. So it probably should look like this one, but maybe sideways or something. All right, so it only depends on mark off y being 1 and -1 and maybe -2. Okay, when y is 1, the vector will be 1, 0. So okay, over here would be -1, 0. So same length, but like that. And then down here where it was -2, it would be longer. Right, so just go twice as long. And something about like that. The next set of problems is determine if the vector field is conservative. And so that's going to be, okay, we saw the theorem. It was if my equals nx. So if we've got like f equaling m and n, because it's a two-dimensional vector field, and we've got the partial of m with respect to y equaling the partial of n with respect to x, then f is the gradient of something else. Okay, but we're just checking to see if it is or isn't. We're not finding the potential function, although we could. Okay, so for number 7, okay, we've got this, and so we're going to say, all right, this is m and this is n. So my equals 15 times 3 is 45 y to the 2. I don't think we're going to be able to take the derivative of this with respect to x and get 45 y to the 2, but I'll try. And x is just, okay, well, this is just a constant from the -5y squared with respect to x, so it's going to be -5y squared. Okay, meaning that since these are not the same, it's not conservative. Alright, this next one is 12xy and 6x squared plus 6y squared. And so we're just going to check my, is it equal to nx? I think, yeah, it looks like it's going to be. So my is the derivative of this thing with respect to y is going to be 12x. And nx is going to be, well, also 12x and 0. So I'm going to say, yes, it is conservative, and I could potentially find a potential function for it. But he didn't ask me to, so I'm not going to. Okay. Next, okay, here are two conservative ones, and we are going to find the potential function. Okay, so so we've got this one. Yeah, that'll be better. And okay, so I'm going to take the derivative of each of these and just make sure that it's conservative, and I'm not totally convinced by looking at it. So y, I'm going to take the derivative of this first part with respect to y first and leave the other thing the same. Then I'm going to add in, leaving this the same, taking the derivative of that with respect to y, and that would be e to the x squared y times 2x for the chain rule. Wait, no, that would be times an x squared for the chain rule. Yeah, because I was taking that with respect to y. So that x squared would be a constant. All right, and x is going to be 2x e to the x squared y. That's promising. Plus, okay, leave this x squared the same. Take the derivative of e to the x squared y with respect to x, and that's going to incur a 2xy. Oh, okay. It does work out. I think I might need more paper to figure out the potential function, but it'll be all right. Okay, so the potential function is an antiderivative for this with respect to x. Okay, which would be, oh, okay, this is like a, this is one I could use u substitution, but I think I'm just going to be like trying to look at it. Maybe I won't. Maybe I'll just spell it out for you. All right, so I'm going to let u equal x squared y. So that du is going to be, okay, with respect to x, it's going to be 2xy dx. Okay, and so that's exactly what I've got. So I've basically got e to the u du. Its antiderivative is going to be e to the u. So I've got e to the x squared y plus some function that may only depend on y. Okay. And then on the other hand, I need more paper. See that f is also equal to an antiderivative of this term with respect to y. All right, well, with respect to y, this thing's going to be its own antiderivative. Oh, maybe we need to, like, x squared's a constant, so if it was e to the 2y, I'd have half e to the 2y. Since x squared's a constant, I'm going to divide by x squared, and I'll just have e to the x squared y. Some other function that may only depend on x, but if it existed, I'd see it over here. And this g of y, if it existed, I'd see it over here. So I know that my potential function is f of x and y equals e to the x squared y plus maybe some constant c. Okay, and that will be the potential function. And the last one is this one, e to the y sine x, negative e to the y cosine x. All right. And I don't know, I'm not too good. You might be able to just look at this and figure out the potential function. If you can, then good for you. Okay. But I'm going to just say, all right, I can see that the derivative of this with respect to y is going to be e to the y sine x, and the derivative of this with respect to x is also going to be e to the y sine x, so I don't really need to check and see if it's conservative. I can just see it is. So I'm going to say f is an antiderivative for e to the y sine x with respect to x, and f is an antiderivative for negative e to the y cosine x with respect to y. Oh, that's interesting. Yeah, I believe it. Okay, I'm just not sure how this is going to go. Okay, with respect to x, I'm going to take an antiderivative, and I'll have negative cosine x times e to the y. Maybe plus some function that only depends on y. And then over here, well, with respect to y, e to the y is its own antiderivative, so I'll have negative e to the y cosine x plus some function that only depends on x. But again, I would see this function that depended on x over here, and I would see this function that depended on y over there, and I'm not seeing anything, so I know it's just going to be these two pieces plus maybe some constant. So, okay. And yeah, that's all the problems for this set. So thanks for watching.